So let's begin with some fundamentals regarding OSPF. We'll get into the areas here in just a moment. So let's imagine we have these two routers right here, and they are both configured for OSPF, process ID 1, for example, on each of them, and all the interfaces have been associated with area 0. Now, that also is one of the concepts I didn't really grasp on to when I was first learning OSPF like 30 years ago. I thought, oh, a router belongs to an OSPF area, but in reality, when we configure OSPF on a router, what we're doing is we're assigning interfaces to the areas, and that's what makes that router, for example, belong to area 0. If every single interface on that router that's running OSPF is enabled and associated with area 0, also known as the backbone area, that's what makes this router an OSPF backbone router, because all of its interfaces are in the backbone in area 0. And we'll break that into larger areas here in just a moment. But let's imagine that router 1 and router 2 have both been configured. All of their interfaces have been enabled for OSPF and associated with area 0, and they want to go ahead and start neighboring up. They want to build an OSPF full adjacency. Now, what is going to stop that from happening? There's a lot that could go wrong, and so I have an acronym that's going to help us remember adjacencies and what's needed to make it happen, and it's STTAMP, like stamp with 2 T's in it. So if you're ever wondering, okay, what has to match for those two devices to neighbor up, think of stamp, and let me spell them out. The first S is the subnet. They have to agree on what is the network they're both connected to. So if router 1 believes on gig 10 that it's directly connected to the 10.0.12.0/24 network, which it is, and R2 believes that gig 20 is connected to the 10.0.12.0/25, even though it kind of looks like the same network, it's not the exact same network. They have to agree on what that common network is between them if we want to have an OSPF adjacency. The next T is for timers. So in OSPF, they're going to be sending hello messages back and forth, and there are some timers associated with that. And if the timers for the hello interval and the dead interval, if they don't match, they will not neighbor up. And that's true for IPv4 and IPv6 as well. In fact, all of these apply to both IPv4 and IPv6. And here in the topology, let me give you a lay of the land. I've documented the IP subnets in IPv4, but I'm also using that same number, that little X represents the IPv6 subnet address as well. For example, here it'd be 2001 DB8678312, and over here it'd be 2001 DB8678334, etc. So for two neighbors to become fully adjacent in OSPF, they need to agree on the subnet, they need to agree on the timers. Another thing they need to agree on is the type, and that is the network type. And let's talk about that here for a moment. On Ethernet, the default network type for OSPF is broadcast. Now, it's funny, I think it's kind of funny, that they don't really use broadcast to find each other. They're using multicast. And those multicasts for IPv4 would be 224.0.0.5. That's an IP address used to reach any OSPF router on that local segment. And 224.0.0.6 is the IP address we'd use to reach and forward information on that local segment to a DR, which also includes a backup designated router. But it's called broadcast with the idea that they can dynamically find each other without specifically pointing in the config to a neighbor's IP address. Other options regarding the network type would be non-broadcast, where it would require additional config. Another option would be point-to-point, which doesn't use a DR at all on the segment. Another option would be point to multipoint, which also does not use a DR. So in addition to having the timers match, we also need to make sure they agree on, first of all, whether they're expecting to have a DR in the case of broadcast or not have a DR in the case of point-to-point. So the best practice is to make sure we're using the correct network type. And when we do that, the defaults for the network type is also going to drive the defaults for the hello and dead intervals. All right, so let me clean that up a little bit. The A is for area. So they need to agree on a couple things. They need to agree on the area ID. They also need to agree on the type, the area type. So this is a good chance for us to discuss different area types in OSPF. So let's talk about this topology right here. In fact, let's back it off just a second. Let me clean this up a little bit. And I'm going to go ahead and draw one giant area 0. Another interesting note here, so instead of area 1, was called the whole thing area 0. So all the interfaces on all the routers are associated with area 0. The challenge here, and well actually with just 8 routers, not a big deal, but let's imagine we had 80 routers. If we had 80 routers, there's little LSAs, link state advertisements, that are being generated by these routers. So an LSA type 1 is called a router LSA. Think of it like a little advertisement that tells all about the router. So R1's generating its own LSA type 1, and that's being propagated to all the other routers in the area. Router 2 is generating LSA type 1s, and those LSA type 1s are describing which networks we're connected to. And the benefit is that if every other router in the area sees every other LSA type 1, they'll have a perfect picture, like a big puzzle of all the interfaces, how they're connected, and a router can then use that to build this best path information for forwarding packets and add that route then to the routing table. Now, if R7 was at a branch office or something, we probably don't want all the LSAs from every single other router to be forwarded down to R7 because we might be using up some bandwidth we don't need to use. Also, R7 may not need all that detail about every single other router. So in larger environments where we have dozens or hundreds of routers, instead of using one giant backbone area, we're going to carve it up into multiple different areas. And that would look something like this topology right here, where we have the area 0, the backbone area. So in the backbone area on R1, we've associated gig 00, 10, 20, and on R2, gig 20, 10, and on R4, gig 20, FA4/1, and on R3, FA4/0, and gig 10, and we've associated all those with area 0. Now, one of the rules, if you want to have multiple areas, for example, area 1 here and area 2 here, we need to have at least one router that's connecting the non-backbone areas to the backbone. So let's start here with area 1. Router 3 has two interfaces associated with area 0, and if we associate this interface right here, FA4/1 with area 1, boom! Then we can have R3 act as a gateway between all the networks here and forwarding traffic either to the backbone area or onto area 2. So here on R5, this interface will be assigned to area 1 there too, area 1, and area 1. And again, it's the interfaces that are associated with the area, not the actual router itself, because R1 is a backbone router because all of its interfaces are in area 0. R7 and R5 have all their interfaces in area 1, but this guy, R3, acting as the border router between the backbone area and area 1, it has a special name as a result of having interfaces in the backbone and also in area 1, and it's called an area border router. And with an area border router, what it does is going to generate LSA type 3s. And the name for that LSA type 3 coming from the ABR is a summary LSA. And the benefit of a summary LSA is that it has information, for example, about the 10.0.13 network and 10.0.12 and 10.0.24 and 10.0.34, and also information about the network 10.2.46, etc. And it can forward all those individual routes down into area 1. So R7 and R5 can know about those routes, but it's kind of a summary in the sense that it doesn't have to know, these routers don't have to know all the details about the LSA type 1s and all the other details about those routers. All they know is that those routes are reachable through the area border router. So in this case, R7, if we had, for example, 80 routers and most of those routers were in different areas, R7 would not have to see or have propagated the LSA type 1s from any of these backbone routers like R1, R2, R4, or any of the other dozens or hundreds of routers because it's in a different area. That's one of the benefits of chopping up OSPF into logical areas or sub areas. Also, while we're talking about LSAs, let's also add an LSA type 2. And an LSA type 2 is referred to as a network LSA. And that's generated by a designated router on a segment. So for example, let's go over here to R2 and R4. One of these two routers is going to be the designated router for the 10.0.24 network for this segment. So I'm going to put in parentheses, DR generates that network LSA that describes that network. So this is the type right here. So the LSA type 1 is generated by each router. By setting up multiple areas, we're controlling the reach and span of those LSA type 1s. So for example, the LSA type 1s from R6 are never going to be advertised here in area 1 because it's a completely different area. And that frees up CPU and resources on R5 and other routers in this area because they don't have to process it or look at that information. Same thing about the DRs coming from a different area. So for an LSA type 2, for example, let's say R8 is the designated router that's generating an LSA type 2 describing that network. That LSA type 2 is never going to be propagated over into area 1 because area 1 doesn't need that information because it's getting summary route information from the ABR that describes how to get to all those given networks without the additional burden of processing the individual LSAs. Think of it like less information is more. So the summary route are advertised by area border routers. And those are advertised, for example, R3 would be advertising summaries. Think of it like the information, the routes for 13, 12, 24, 34, etc. And it would be advertising those routes, but it wouldn't be forwarding down the LSA type 1s and type 2s into area 1 from any of those other areas, because these routers here don't need that information because they have the summary routes. So that leads me to the area type. And as we've described it so far, area 0 here would be a normal area, the backbone area. Area 1 would be a normal area. Area 2 would be a normal area. So what exactly is a unnormal area? So as far as areas go, we'll jot down normal. What normal means is that we could take an external route, for example, EAGRP or BGP or static route, and we could redistribute it into OSPF in that area. That's an example of what we could do in a normal area. And so we might have that feature and that ability and need to do that in the backbone area. However, let's imagine that area 1 and area 2 are being used in two separate geographical locations, and we don't need to do redistribution in those areas. We want to simplify it. What we could do is we can make those areas a stub area. So a stub area says, okay, we're not allowing the redistribution of other routes into OSPF, for example, from BGP or from EAGRP or from static routes, which is great. And there's also an option of something called a totally stubby area. So let's imagine we made these areas a totally stubby area, both of them. What that means is these two routers, R3 and R4, which are the area border routers for area 1 and 2 respectively, with a totally stubby area, they are not going to forward in even the summary routes. So area 1 here and the routers here wouldn't learn about 10.0.12 and 10.0.34 or anything else because the ABR in a totally stubby area is not sending those routes. Now, the problem with a totally stubby area is that if we are not receiving, if R5 has no idea about the 10.0.12 and 10.0.24 network and other networks, how in the world are these routers going to know how to forward if they need to forward a packet to any of those networks? And the answer is, in a totally stubby area, we can also advertise a default route into OSPF. So that way, R5 and R7, even though they're not getting these summary routes regarding all the individual routes from the other OSPF areas, they are getting a default route, and then they can forward packets using that default route in the direction of the ABR. And again, that's going to reduce the number of LSAs here in area 1 and area 2 if they're both totally stubby, because they're now not receiving LSA type 1s from other areas, they're not receiving LSA type 2s from other areas, and they're not receiving LSA type 3 summary LSAs, with the exception of the default route that's being injected into the area by the ABR. So why the big discussion, Keith, regarding types? Well, the answer is that type has to match. If this interface here thinks it's a normal area, and this interface here thinks it's a totally stubby area, that will prevent them from neighboring up. So that's why the area ID, for example, area 1, has to match, and the type. In this example, just a stub area or a normal area, whatever we set up, it has to match between those two interfaces on that common segment. And there's also an option for something called a not so stubby area, which is where you want to have this be like a stub area, but you want to make an exception to be able to inject or redistribute routes into that area. So for further discussion regarding configuring and working with and playing with stub and totally stubby and not so stubby areas, we're going to save those discussions as part of a skill in another course, very likely an RC. But I wanted you to be aware of some of the options here because the type has to match if we want to neighbor up with another device on that same segment. So back to our mnemonic of STAMP, the M is for MTU. Now, if you have two routers, the same model or similar models, it's very likely the MTU for Ethernet is going to be 1500 bytes, no problem. However, let's say we're pairing up with a multi-layer switch and a Cisco Catalyst, whatever, and the MTU on the router is 1500 and the multi-layer switch, the MTU is 1504. That will cause a problem if the MTU isn't the same size. And that's kind of frustrating because you can ping and connect back and forth. However, they won't neighbor up if the MTU doesn't agree. So we could either manipulate the MTU here and make it match 1500, or we could configure OSPF to ignore the MTU and simply neighbor up anyway. And then the P is for password. Now, I use password so the mnemonic would work. However, really what that is authentication. So the authentication method between two routers on the same segment, that has to match. So for R1 and R3 to neighbor up, they need to be specifying using the same type of authentication. So if one is set for plain text and the other is set to MD5, that's not going to fly. And further, if they agree on the type of authentication, we also need to make sure if we're using a password, that password matches on both sides. Or in the case of MD5, the hash of that password matches on both sides. All right, so let's clean that up and let's take a look at the metrics involved with OSPF and how it decides on the best path. For the path selection for OSPF, it uses a metric, and that metric is cost. And just like going to shop at a store, if we had two comparable products, they were virtually identical, except the cost was different, we choose the lowest cost. And that's what OSPF does. So each of our interfaces has an associated cost. Now, by default, it's unfortunate, but it's kind of a legacy thing. There is something called an auto cost reference bandwidth. We've talked about that in our CCNA courses, and it's also relevant here because the default is 100 megabits per second. And a few decades ago, it wasn't a problem using that value when we had much slower speed networks. However, the auto cost reference bandwidth works like this. We take the reference bandwidth and we take our actual interface bandwidth. Let's take fast Ethernet, which is 100 megabits per second. In the case of fast Ethernet, so fast Ethernet, if we divide 100 into 100, it equals 1. So that would have a cost of 1. Well, let's go ahead and do that same math with gigabit. So the reference bandwidth, again, if it's 100, and the interface bandwidth is 1,000, meaning 1,000 megabits per second, 1,000 going into 100 is 0.1. However, we're going to round it up. So for gigabit Ethernet, by default, if we're using the default reference bandwidth, the cost of a gigabit link is 1. So it kind of makes OSPF blind to the difference between fast Ethernet and anything faster. So ideally, what we'd want to do is increase the reference bandwidth. So if in this topology, we could set it to 1,000, and that would make our gigabit links look like a cost of 1, and our fast Ethernet look like a cost of 10. However, in environments where you have 10 gig and 40 gig and higher, you may want to set it to even higher than that. So in the lab environment, that's what we're going to be doing consistently. We're going to set the auto cost reference bandwidth to 1,000, and that way gigabit links will look like a cost of 1. Fast Ethernet look like a cost of 10. Let me document that real quick. And the serial links I have set at 64, the bandwidth set to 64 kilobits per second. And so their value for these serial links, actually we're not using this one, and we're not using this one, but I do have OSPF enabled on these two. So the cost of that serial link, I'll put it right here, is $15,625. And we can see that once OSPF is configured with the show IP OSPF interface brief for IPv4. And so if we were going to calculate, for example, from the perspective of R8, its cost to get to the 10.0.1 network, assuming the network's converged and all our neighborships are set up. For this target network, the OSPF cost should be, we'll have a 1 here, so 1 plus, and then 15,625 plus, then the best path would be, then the cost be 1 here, and then going through our 2, the cost is 1 there, and then we count the final network, which is 1 here. So it's all the egress interfaces that we're looking at. So going out here for 1, out here for 15,625, here for 1, here for 1, and here for 1, and that's our final destination. So if all those values are correct, that would be a cost from R8's perspective to get to the 10.0.1 network using the best or optimized path. That'd be 15,629. Now, one of the cool things about this set of videos and this skill is that I also have a hands-on lab for you. So in addition to predicting like what we think the cost is going to be, we can also, once it's labbed up, validate that that indeed is the case. And in the event that we have 2 or more routes with equal cost paths with OSPF, it can use equal cost load balancing. Now, one more piece of information I'd like to share in this overview is that there is more than just one way to configure OSPF, meaning we can use the traditional method for setting up OSPF for IPv4. There's also a traditional method for IPv6, and we also can use a OSPF v3 option for configuring both IPv4 and IPv6, or either IPv4 or IPv6, using the concept of address families. Not too different from actually how we configured it with EIGRP in a previous skill. So we're going to have a separate set of videos on configuring OSPF version 3 and working with it. So for this set of videos, I'm going to actually walk you through examples of configuring IPv4 traditionally and IPv6 with OSPF using this topology, with the interfaces shown in green here in area 0, and the interfaces shown in blue here in area 1, and the interfaces over here in whatever this color is, kind of a pinkish thing, in area 2. And as we go through this together as part of this set of videos, you'll have the opportunity of seeing how it's configured and also doing the configuration in the hands-on lab. But most importantly, regarding understanding OSPF, is we can actually see and take a look at the results. We can take a look at the LSAs. We can practice with the show commands to verify that what we think is happening is indeed happening with OSPF. So with that in mind, in the next video, I'd like to demonstrate for you the implementation of OSPF with IPv4 using the traditional option and using 3 areas: the backbone area, area 0, and then area 1 and area 2 connected to the backbone through area border routers. Hey, thanks for watching, and subscribe right here to get the latest information from CBT Nuggets. And if you're new to or considering a career in the world of IT, head on over to CBT Nuggets and sign up for a free trial.